Hello everyone, my name is Gurnoor Singh and this is my video demonstration for complex threading task using the quicksort algorithm. The first demonstration that I will provide here is for the quicksort algorithm using a sequential method. And as you guys can see that I have my program here which has three major components. The first we have the header files that will use all the libraries that are required. Then I have the partition function. Then we have the quicksort function and then the main program where the whole execution takes place. So within the partition function, what I've done here is actually taken the last element of the array as my pivot. And then I use this for loop here what will it do is basically divide the whole array into two parts. That is, left side of the array will have the elements, as you guys can see, that will be less than the size of the pivot. And then the right side of the array will consist of the elements that are larger than the pivot. And then afterwards, we have the swap function here again being used that will reset the pivot position and index for the correct sorting to take place again. And afterwards, what we do is move towards a quick sort function here. And within the quicksort function, what happens is that once array is divided into two parts, uh, we have the quicksort for the left side and the right side. And what it does is basically performs a recursion within the algorithm, and then it further sorts the subsets that have been divided into two parts and sorts them further and further until we have an algorithm that is we have a data set, sorry, that is perfectly sorted. And that is checked through this condition here, if low is less than high. And afterwards, we have a main execution being carried out. And here the array size has been given by me, that is 100,000 numbers. And this array size is basically filled with random integers through this R&D function used by this loop. And then we basically call a quick sort function in order to sort this array. And yeah, afterwards, you guys can see that the execution time is being measured by the high resolution clock. It starts here, stops here, and then is basically displayed onto the terminal. So what I'll do is here, take my new terminal, and I'll go g++ code 1 dot cpp minus o code 1 dot exe / code 1. And I will run this program. And it takes about 16 milliseconds for array size of about like 100,000 numbers. But let's say if I consider a real data set and increase it to about 1 million, what happens? So when it sequentially performs this sorting, it takes about 231 milliseconds. And so yeah, that's how this program does get executed sequentially. And what I'll do now is actually move forward to the B part of my task and show how this program was executed parallelly. Go folder, go to. So yeah, over here in this section, what I've done here is I used omp.h library to parallelize this program. And basically my partition function remains the same, but within my quicksort function, there are some changes. That is, I declare an integer depth. Will it do is basically control the amount of threads that are being generated, so that is not a large number of threads. As we guys can see that the algorithm basically is a recursive algorithm, so it will generate more threads in order to call itself again and again and sort the subsets that are there. And in order to avoid a large number of threads, we have the depth uh, condition here. And as you guys can see, the pragma OMP parallel section is used in order to basically divides these two paths, left and right side, into two parallel threads. And these threads will further divide and sort the whole data set. Afterwards, I have my array size. And within this section here, I've again declare this as a pragma OMP parallel, basically calling the library again here in order to divide the task into threads. And here a single no wait has been used so that the initial call that is being made to generate threads is just by a single thread, and it further divides rather than just a large number of threads calling itself. So the program starts from a single thread, divides itself, and then sorts the whole algorithm. And what I'll do here is just call this again. So for this one, g++ minus f open mp 2.cpp minus o2.exe. Yeah. Slash exe. Yeah. So about 6 milliseconds for a size of 100,000. And if I, let's say, make it 1,000,000, that is 10 times more. I get about 38 milliseconds. And when I essentially compare these two outputs to my sequential program took about like 14, 15 milliseconds for 100,000 um, integers, and then about 231 milliseconds for about 1,000,000 integers. And as you guys can see that my parallel program perfectly beats the sequential one because of the number of threads that it uses in order to solve the algorithm effectively. And hence we can see that parallel programming is much more efficient sort of programming in order in case of large data sets. So yeah, this is the overall demonstration for my complex threading task. And yeah, thank you.